Professor, did you ever figure out that question that we were working on
I'm still
yesterday?
work. I'm still working on it. I was hoping I could knock it out tonight, but I ended up getting a little bit stopped that night, and then I didn't have any time today. So I'm hoping I can
Okay.
knock it off tonight. But one of my students, I mentioned it to him because I was going to try to work it in class, but we ended up not having enough time. He said he was able to find solutions, but he's not sure he really understood it. So I know you can at least find, obviously, the answers online. But he said the answers that he found online were actually huge steps were skipped. So that
Okay, I got you.
that's sort of the
Uh,
norm. But I'm hoping I might be able to knock it out like right after class, and then I can just send a photo of it to everybody, or maybe even make a little video and send it to everybody just so you'll know. I also got shocked with a little bit more information. Did you see the email I sent out today?
no, let me go ahead and look at that. Was it about the exam?
Yeah. Basically, I looked at our schedule about 2 weeks ago because I was thinking originally that it was the 29th, and I just wanted to double check. So a couple of weeks ago, I checked and I pulled up academic calendars on our website, and I accidentally looked at the end of the third 5 week short semester, and that's May 3rd. The end of the 15-week semester, which is what we're in, is March 29th. So that forced me to basically shift everything back in time a little bit. So I'm still having the same 29 day date as well as time periods there, but I've also now offered one on the Wednesday before that.
Because I don't, aren't we supposed to take for the people online that have the Thursday night class, are we supposed to take that in person to that one?
Yeah, you're supposed to take it in person, but with your lab instructor.
Okay, so that is that would that be on the following Thursday or would that be on the Thursday before the
I would
29th?
ask her because she normally the way she does it is she the week before she has her comprehensive lab final, and then the very last day has her actual lab excuse me, her actual course final.
Oh, okay. All right, yeah, then I'll ask her
Her when
then.
she's got it scheduled. I haven't sent an email to her, but I'll be sending a text message or something tonight to find out. But like I said, I usually don't ask before in case I screw things up. So I usually wait until after I tell everybody before I actually ask the other instructor. So definitely ask her.
Okay.
All right, got more people coming in. Okay, I got two of my Hannahs, not three of my Hannahs, but I got two of them.
I didn't know there was a third one.
Yeah, there's a third one. They're actually in a different class. It's just, so luckily it's not quite as bad as it could be. And actually, y'all are very distinct, different people, so that makes it a little easier. The problem is you're mostly a face to face. I mean, not face to face, but online. So that makes it a little harder because I don't have a face to associate it with it. But luckily, I got you in my lab, so I know your face. At least I think that's the one I know. Your voice sounded familiar.
Yeah, that was me, Hannah Keen. My
Okay,
camera's not working today for whatever reason.
that's cool. The first semester I did this, I told you my one of my students looked up and their camera was working. It was like 3 o'clock in the afternoon. She's drinking a big old glass of wine. I love that. I thought it was hilarious. Like, at least let's not show you drinking the wine in class because that's probably not appropriate.
That was one of your students?
Yeah, yeah. And it was like the very first day. It was like right after we got into the pandemic situation where they said, "Okay, you're out to teach from home online." And it's the very first class. I was like, "Oh, okay, I guess that's what we're gonna do now."
Oh my gosh.
I don't blame her. The heck, man, you sitting around the house, you got kids, you got sickness, you ain't gonna get out of the house for 6 months. I get you. uh, all right. Well, it looks like we've got 8 of us here, and it is 1 minute late. So let's go ahead and get started. Last time we actually did finish chapter 11. First off, I want to tell everybody I did send you an email, and I saw one person replied to the email. I haven't had a chance to reply to them, even though I saw like the first sentence that they wrote. So that email was specifically about people that are taking my face-to-face lab and are the people that are taking my face-to-face class. Those people count as well. They are all just automatically allowed to take my exam at my lab times. And what I discovered, because one of my students was paying attention to the academic calendar, which I had done as well, but forgotten. And I was just telling Keegan a second ago, Caden, sorry. I was telling Caden a couple weeks ago, I got a little nervous about the due date because I'm teaching at another school too, and they have a different due date. So I looked it up, and when I looked, I evidently was looking at the third 5 week semester, and that 5 week semester ends on May 3rd. So all that for the last 2 weeks, I've been thinking class ended on May 3rd, which was nice because I got a couple extra days and didn't know why I got them. But then this morning he asked me about it, and I was like, "Ah, crap!" I looked it up, and sure enough, he was right. It was the 29th. So I didn't want to go back on my word and say you can't take it on the 29th. So the exam's now on the 29th, but I'm also doing it on the Wednesday before, which I put in the email. I'm pretty sure that was the 24th. It's either 23rd or 24th, but it's Wednesday. And I have a bunch of different times you can come in to take it. So you're open to either one of those. Uh, Now, if you just can't take it at the nighttime class with your lab instructor, as long as the lab instructor approves it, I can have you tested in my testing center as well, but you're not required to. But the general rule is if you're taking someone else's lab, you take it when they say. I haven't talked to Maria yet. I'm actually going Marisia. I don't know exactly how she pronounces it. Even though I've talked to her a lot, I'm just really bad with remembering names. But I haven't talked to her yet regarding this in the recent month or so. So I'm going to send her a text tonight and find out. But that's what you guys need to do is just find out on her syllabus what day did she say you're going to take the final. If she didn't say that, just drop her an email, or she might actually drop you an email after I send the email to her. Okay. So what I was saying was we've now finished chapter 11. I've given you all the material that's really important. I will be making the practice final tonight. So you'll have that ready and you can start taking it. And what I've done is I've pared back some of the chapter stuff that I'm covering specifically because I did it so quickly with chapters 14 and 15 and a little quickly with chapter 11. So chapters 11, 14, and 15 in the bank that you use for the practice final will have a lot fewer problems than it normally does. Normally, a single chapter will have anywhere from 50 to 90 problems. This one will probably have on the order of 20. So for each of those chapters, and chapter 15 might even have less. So anyways, I just want to let you guys know that. So we're starting now chapter 14, which is called oscillations, and oscillations is just another word for vibration. So if you think of something that vibrates, you can say it's not only vibrating, it's oscillating. And that's how you pronounce that word. I've heard people trying to pronounce that C in public places before. So I just, I can tell, oh, you never had a physics class. That's obvious. I saw someone actually at a hardware store. She asked me for help because I was wearing a shirt that matched the same color as the hardware company. So she thought I worked there, and she said, "What's this oscillating fan?" So, anyways, that's a common thing. People don't know that word, but that's the word right there. oscillations. And what we're studying is vibratory or oscillatory motion. That's two other versions for it. Call it adjective versions of the word vibrate or oscillate. So vibratory or oscillatory motion is another word for it. And what I tell you is that harmonic motion is motion that repeats itself over time. And you're normally used to seeing, like, if you pull a mass down on the end of a spring, you'll pull it down and then let it go, and it'll go up, down, up, down, up, down, up, down. And if you plotted that on a graph, it would look like y equals sine x, basically. So they call that sinusoidal motion as well. Then we define a term like period as the smallest time interval over which the motion repeats itself. So let me go ahead, now that I've given you that little intro, I'm going to go ahead and share my screen. There's a lot of neat little things you can do with this stuff that makes life kind of a little bit easier. For instance, you can, predict how things are going to behave, even though you don't really understand the mechanism that's making it. For instance, one example your book has is a big engine or tool of some sort is in a room, and it's oscillating rather rapidly, and it's causing the whole floor to shake up and down, up and down, up and down. And all they tell you is it's doing it at 10 hertz. And what they want you to do is figure out what's the spring stiffness of the floor, and from that, what also is the maximum acceleration that it'll have. So just from knowing that it's about 10 hertz and that it repeats itself, you can assume over some period of time it's going to behave like oscillatory or sinusoidal motion. And from that, you can go ahead and use the equations that we learned here and get useful data. So for instance, when I did structural engineering work, what we did, at least for design of seismic loads, which is earthquakes and stuff like that, is you usually take a multiple of gravitational acceleration. So just knowing an acceleration allows you the benefit of using Newton's second law to calculate a force. Once you have the acceleration, which gives you the force, then you can calculate, how big a particular beam has to be, a shear wall, that kind of stuff, struts, drag struts, all that kind of stuff. So it is very helpful. So here's what I've written down. I tried to not make it where it's always thought of as just sinusoidal. So for instance, harmonic motion is motion that repeats over time. So I drew a position versus time graph, and notice that's this little, hook backwards L shaped, or excuse me, L with a hook on it shape is repeating itself in time. And the smallest time interval over which it repeats itself is called the period. And of course, that's given the symbol T, which we've run into before, and it's measured in units of seconds. Obviously, it can be measured in units of hours and minutes and days and stuff like that too, but generally we use seconds. There's a concept called frequency, which you ran into before to some extent, and it's really the number of cycles that occur every second. And what I did was in parentheses, which maybe I should have put in parentheses after it as a note, I said the motion that repeats itself is called a cycle if it is the smallest part that repeats itself. So, for instance, if you look at the sine wave, when you graph y equals sine x, it looks like that. Notice it doesn't start to repeat itself until right there. So that little part from there to there is the period. Again, this is going on the assumption that this axis is a time axis. This axis can be anything else, but it's normally a space, of course. So that's a period. Notice that's also the time from one peak to the next. It's also the time from one trough to the next. And it's also, if you take a random point, it's from here, skip one to another random point that's equal in height. Notice it is not this point right here, okay? The reason why is if you imagine this graph was actually like plywood and it's been laid down as like some kind of floor or a skating ramp or something like that, if you poured water on that purple dot, it would move to the left. If you poured water on this blue dot, it would pour to the right. So those two points are not identical. If you go to the next one, though, it would also pour to the right. So that really is another unit of a period. So the period would be this long as well. Okay. So that's what a period is. I'll also say that this distance from the midline up to the peak, or from the midline down to the trough, is called the amplitude. So this is the amplitude. Actually, probably should have wrote that in black anyways. And we spell that AMPLITUDE just in case anybody didn't know. I don't think spelling's y'all's problem. I know for a fact spelling's my issue, but I used to be good at it. I'm not too much anymore because I've been writing with computers so long. So that's the amplitude, and the amplitude can vary depending on what kind of stuff we're talking about. So, for instance, what we call a simple pendulum is like this mass going back and forth. Well, the easiest way to measure this mass going back and forth is to measure the angle it makes with the vertical. In that case, then the amplitude would be in radians or degrees or something like that. So that's one case. In the mass on a spring, it could be centimeters or meters. Distance would be the normal thing. And quite often, amplitude is normally meters. But we'll later learn about other types of vibratory, oscillatory motion, for instance, wave motion. And the amplitude of those can vary quite a bit. So, for instance, a sound wave is technically a pressure wave. And therefore, if you really wanted to measure the amplitude of the sound wave, you would find that the amplitude is measured in newtons per square meter, or pressure. Pressure is a force per unit area, so it's newtons per square meter, which is also called a Pascal. Uh, Pressure waves can also be created, of course, from bombs. I was telling my class earlier today, two horrible cases. Obviously, it's not a whole lot of wonderful stuff that comes out of bombs, other than sometimes they can end a war. But for instance, in the Murrah Federal bombing, where Timothy McVeigh blew up a building, that was part of what he used. He had basically a Ryder truck that he had packed full of explosives, uh, well, stuff that was made explosive. And when it exploded, it actually put out a pressure wave that not only went up, it also went down, bounced off the ground, and came back up too. And that 1-2 punch with two different pressure waves caused the whole front of the building to fall down. J. Robert Oppenheimer in the recent movie you've seen probably, he suffered the same dilemma. By the time we finally got to the point where we had figured out all the engineering problems of making a weapon, he made the weapon, and he realized, of course, that it was really horrible. He had started thinking about it before he solved the problems, but still, it was one of those things where it was a discovery. It was a patriotic thing to do to help his, everybody was worried about Hitler, that sort of thing. Uh, but he ultimately decided it was the most god awful thing he'd ever been a part of, and he really didn't want it used ever. But he couldn't get anybody to assure him that it'd never be used. So he said, well, I've got to do what I got to do. And what I got to do is make it seem as awful as it possibly could. So he literally looked for cities where the diameter or the size across the city was just barely larger than the actual explosive blueprint of the bomb. That way, it would literally leave a gaping hole. So, I mean, this is really horrible. I'm not trying to make light of this terrible thing, but when he bombed Hiroshima and Nagasaki, that was the credentials that he was looking for a given city. And he had chosen both of those. Weather messed up some things in one of them, so he had to choose the other. But, anyways, that's exactly what they did. But it's that pressure wave and the fact that he knew it had to be an awful, awful, awful event that hopefully would deter anyone from ever using it again. So he also detonated it on the order of like 100 meters or something above the Earth's surface. So in that case, the explosion first came direct line, hitting the buildings that would blow them outward, but also squish them downward. And then the second explosion would hit it, where it's basically still the same explosion, but that pressure wave would go down, hit the ground first, and then lift up. And that combined 1-2 punch made it literally just completely decimate or destroy all the buildings. Of course, it also destroyed a lot of people and left shadows of people on the walls and stuff like that. But that's another example of a wave, and in that case, a pressure wave. Sonic booms are pressure waves, all those things. But like I said, in each of those cases, you have a different amplitude. Light, for instance, from a head from the sun or from a lamp, that's called electromagnetic radiation. And what that is actually it's an electric field oscillating in one plane. If it's vertically polarized, for instance, that means the electric field's oscillating vertically. And then the magnetic field is oscillating perpendicular to that, always is, and it always obeys this right-hand rule, by the way. So you got an electric field oscillating up and down, a magnetic field oscillating left and right, and then you've got a third mutually perpendicular direction straight ahead. That's the direction of propagation. That's the word we use, propagation, propagation. That's the direction the velocity is going. And it's such that basically if E is going up, then that would be that direction. And the right hand rule would say, okay, I can cross towards B. So B's got to be going to the right. So if the electric field's up, the magnetic field's going to the right. And then by taking your hand and curling it from the direction the electric field was going to the direction the magnetic field is going, leaves my thumb pointing straight ahead. So if the electric field is up while the magnetic field is to the right, then the velocity has to be going to you. So that's another neat thing. In that case, the amplitude is actually, for the electric field, it's either newtons per coulomb or volts per meter. For the magnetic field, it's Teslas. Okay, that's just a unit that we use. Another one's a Gauss you could use. So that's some examples of all the different amplitudes, but you now know what the amplitudes are. And of course, what we also know is that if you're a surfer, for instance, especially if you're surfing really big waves, like you've seen some of those waves that are over 100 foot tall and stuff like that, the surfers ride. What they do and often is you're down in the trough of the previous wave and you look up to the crest of the wave that you're getting ready to ride, hopefully, and you say, okay, well, that looks about 85 feet high. You would call that an 85-foot wave, but we would call that a wave whose amplitude is 42.5 feet. Okay, so keep that in mind too. The distance from the trough to the crest, I didn't even tell you those words, but that's sort of me assuming you know it. So that's the trough, and that's the crest. So the vertical distance between crest and trough is 2 times the amplitude, whereas the distance from the midline to the trough or the midline to the crest is the amplitude. Okay, any questions on that? All right, some other terms we use, like I said, frequency is the number of cycles that occur every second, whereas period is the smallest interval of time over which the motion repeats itself. So if you imagine walking out on a pier, you could see a wave come in and try to imagine, hopefully you've been to an ocean before where you've seen something like this just before or just after a storm. A lot of times the ocean will look nice and slick, but then it'll have a certain number of rollers they just look perfect. They're all parallel, they're smooth, they're equidistant apart. So you see, each one looks like they're maybe 100 feet apart, and then there's another one right behind that, it's 100 feet, another one behind that, it's 100 feet. That's the ideal scenario of looking at a wave, and that's really the mathematical waves that we normally treat. That being said, if you see those kind of rollers coming down and you're on the pier, you can take a stopwatch, and the instant the peak of one wave is directly below you, you start timing. And then you wait and you go through the trough of that wave, and then next comes up the crest of the next wave. As soon as that crest gets under you again, you hit the stop. And that time period is what we call the period. So the period is also the time it takes for the wave to travel one wavelength. That's another way of thinking about it. So if I were to do that on a pier and I found out that it took 8 seconds for one crest to pass me and then the second crest to arrive, that would mean the period is 8 seconds. Now, can someone tell me, if the period of a wave is 8 seconds, how many or what fraction of a wave passes me in a single second? Anyone? I've got the chat window open too, so you can type it if you don't want to do the whole speaker thing. So it's 8 seconds is the time it takes for the crest of one wave to get to me, and then the crest of the next wave to arrive to me. That takes a full 8 seconds. So I'm asking, how many waves pass you by in a single second? Or what fraction of a wave passes you by in a single second?
Is it 1/8?
Exactly, 1/8. And that's not a coincidence. In fact, that was what I was trying to motivate. that tells us, in fact, that frequency is 1 over the period, and that, of course, period is 1 over the frequency. Okay. Notice I said the period is measured in seconds. That's very typical. The frequency is measured in hertz. You've probably heard that word before, at least in station identifications with radio stations, but it's named after a guy whose last name is Carl. No, it's named after a guy whose last name is Hertz. His first name is Heinrich Hertz. But there's also old literature floating around, especially government documents, that instead of using hertz says CPS, which means cycles per second. So that's also another unit that's occasionally used. Okay. If you see cycles per second are hertz, you know you're dealing with frequency. There's also another frequency called the angular frequency that you studied in rotational motion, omega. That's also called the angular speed or angular velocity. That is another type of frequency, but it's strictly, we normally strictly think of it as degrees per second or radians per second. Okay. So sometimes motion doesn't have anything to do with rotation, right? A mass on a spring, in some sense, you can't really see this mass going down, down, that doesn't seem to have anything to do with degrees. Your book actually goes through a whole section where it explains how you can mimic the motion on a spring by thinking of a motion in 2 dimensions that's circular. That's great. But in order to do that, you've got to make the conclusion, as I do here in parentheses, that basically 2 pi radians is 1 cycle. Okay, so if you make that conclusion, just going to say, hey, 2 pi radians is 1 cycle, then even for something like a mass on the spring, you can say cycles per second, and you can talk about omega having units of radians per second, that sort of thing. So I want to put down here that omega, remember, this is the symbol we use when we're trying to express the units. Omega is what occurs when you have radians per second. You might even say degrees per second. And you might even say revolutions per minute. But I'm sort of a purist, so I pretty much only say it's this if I'm going to call it omega. I usually reserve terms like degrees per second and revolutions per minute. I sort of think of them as a frequency. But if, as long as they have something like a angular part of it, then it's okay to call it that. No one's going to say, no, you're wrong. Okay. With that in mind, we now have a relationship between frequency and period, and between period and frequency. We also have a relationship between omega and frequency, and I suspect you already know that. And it's just basically a conversion of cycles per second, which is what frequency is, to radians per second. And of course, there's 2 pi radians in a single cycle. So if I had F in cycles per second, I would want to multiply it by 2 pi radians divided by 1 cycle. That's why the formula is omega equals 2 pi F. Does that make sense? Now I can also use the top expression and find out that omega is also 2 pi over the period. So that comes in handy as well. Now we can also make one more jump, and that other jump is that, as I told you, if I'm sitting on the pier and I watch one wave come by and the peak is right under me and I start timing it, then the trough goes by and then the next peak arrives, then a whole cycle has passed me by. Okay. That means that the distance traveled is exactly the length from, and this is length, meaning in like meters and stuff, not seconds. The length has passed me by in a time period of one period. So if you want to calculate the average velocity, which waves generally move at a constant velocity, not an acceleration, then you could say velocity is equal to delta x over delta t. And I just told you guys that delta x was the full wavelength. So just to clarify what that means, if instead of plotting x as a function of time, you could plot x as a function of, let's say, z, then your wave would look like this. Again, it's still just a sine wave, but the minimum distance over which it repeats itself is called the wavelength, and we give that the Greek letter lambda. Okay, so the wavelength is lambda, and it's the minimal distance over which the cycle is repeated. So I'm trying to say exactly the same thing as I said for period, but using a distance instead of a time. And the units for wavelength are, of course, normally just plain meters. So now that I have that, I can say, based on what Mr. Younger told you about the wave going under me at the pier, you know the distance traveled was lambda, and you know the time taken, that 8 seconds, was the period. So we now have a relationship for the velocity of the wave. This is called like the baby wave equation. Uh, but we can make it even simpler by making use of the fact that 1 over t is equal to frequency. So we could also say lambda times f. So we get a new expression, velocity equals wavelength times frequency, or velocity equals wavelength over period. So these are both very important equations. I'll call them again the baby wave equation. Okay. These equations right here are also important. That other one was just sort of a derivation. And that's about it. So that's sort of the motion that we're looking at. Now, this is oscillatory motion. When we get into chapter 15, that's actually going to handle what we call wave motion. So the difference with wave motion and harmonic motion is harmonic motion repeats itself in time. Wave motion transports energy from one place to another without necessarily transporting mass from that one place to another, and it also repeats itself in space. So it has both a wavelength and a period, which are synonymous with each other. One's sort of the time version of wavelength, and the other one's the distance version of wavelength. So the wavelength's not all that relevant right now. It's more relevant once we get to the wave motion, but I just wanted you to see the parallel between period and wavelength. Anybody have any questions on any of that? Okay, so you've already seen Hooke's law, and Hooke's law is this, and this is the same Hooke that I told my students when Newton said, "If I have seen further than others, it's only because I stood on the shoulders of giants," which sounds really modest and sweet and stuff like that. What we've told you is it's actually quite the opposite. He was being arrogant and he was being condescending because he said it in front of the Royal Society, the president of which had a short man's complex, and his name was Robert Hooke. So it's that guy. And he's basically saying, if I have seen further than others, it's because I stood on the shoulders of giants, not hobbits like you, Mr. Hooke. Specifically because they had an ongoing fight where Hooke just kept blaming him for stealing everything that Newton published or accomplished. Hooke said, "You stole that from me." Newton was a hermit. He didn't steal. I doubt he stole anything from Hooke, to be honest with you. But anyways, that's the Hooke guy. And Hooke tells us that if you stretch a spring by an amount X, the spring will have a characteristic spring constant called K, and the force the spring will apply to you when you stretch it a distance X is negative Kx. Now that negative has to be there if you're going to take and plug this equation and other equations, but a lot of times you just need the magnitude so you can drop the negative. The reason why it has to be there, though, is imagine this. Let's I'm going to draw a wall attached to which is a spring, and sitting on which, on the floor of which, is a mass, and we're going to assume that has zero friction. Okay, and this, for instance, might be the equilibrium position. So this would be what we call x equals 0, which is the equilibrium position. Okay, so it might be smart for us, for instance, to put a coordinate system right here, and that'll be our x-axis, that'll be our y-axis, even though we won't need the y-axis at all. But you can see, if I were to stretch the spring such that the mass is now over here, you can see that the mass has moved a distance x. Notice that x is a positive number, right? Because it's on the right-hand side of the origin. It's in the direction that the positive x is pointing, positive x-axis is pointing. So if I put a positive number in there and I multiply it by positive k, the spring constants are always positive. That's what that's called, spring constant. And then I multiply that by -1, I get a force that's negative, and that's exactly what's going on. If I stretch the spring to the right, the force is pulling back to the left. So that's why that negative's in there. Does that make sense to everyone? Now, if we take this as frictionless, what's going to happen, which obviously frictionless isn't a real thing, but we can get it pretty close with air tables or ice skating rinks and stuff like that. But if I were to stretch that out to, let's say, a distance, let's call it x0. So I just put a 0 on it. If I did that and then I released it, what would happen is that spring would start pulling the mass to the left, to the left, to the left. But as it got a little closer to the origin, the force would go down, and the force would go down more as it got closer, and more as it got closer, and more as it got closer. In fact, when it reached that x equals 0 spot, the force would come to a 0. At that point, the box or the block has actually sped up to its maximum speed. So it's going to actually blow through this point right here with a speed V max. Okay. Now, at that point, as soon as it gets to that origin and goes just a micrometer past, now the force is going to push to the right and try to slow it down, slow it down, slow it down. But the further it goes, the bigger the force gets, till eventually it comes to a stop because the force has gotten so big that it stopped it. You know, if it really is frictionless, it's going to come back to a position negative x0. Does that make sense? I'd pulled at x0 and let it go. So it's going to go all the way back to a positive, or excuse me, to a negative x0 before it comes to a stop. But again, at that point, I have v equals 0. And again, at this point, which would be negative x0, that would have v equals 0 as well. At that point, the spring, since it's still pushing to the right, is going to push the mass. It's going to speed up, speed up, speed up, just like it did before, reach its max speed at 0, and then start to slow down, slow down, slow down, reach speed of 0 at positive x0, and it's going to complete that, repeat that over and over and over again. That's just the way motion behaves, or how mass behaves on a spring with no air resistance and no friction. So if you actually made a plot of that, what we would see in this case, I actually started with a maximum position. So I'm going to say it's going to go like this, like this. Like that. And this height right here is x0. And this right here is negative x0. And what we found, in fact, was this point right here has V equal V max. And this point right here has, that's actually V equals negative V max because it's going in the negative direction. And this point right here has V equal positive V max. And this point right here is V equal negative V max again. And this one again is V equal positive V max, so on and so forth. In fact, you'll also discover that the acceleration is a maximum when the stretch is a maximum, because F equals Kx tells you that when the stretch is a maximum, the force is a maximum, and the force has to be equal to m times a. So that means the acceleration is a maximum. So I could put another dot up here and here and here and here and here and here. In this case, it's going to be A equals A max. Now, it's a little harder to tell whether that's positive or negative, but when I take the derivative of this, which really looks like cosine, the derivative of cosine would be negative sine. So the velocity is going to look like this. And then when I take the derivative of negative sine, I get cosine again. So in this case, that's going to be V of t. And then in this case, it's going to go back to positive cosine. So it'll be like this. And therefore, that tells me the acceleration is a maximum positive here. So this is a positive A. This is A equals negative A max, so on and so forth with all that. Okay, so that's what we know about the motion in general, just from everyday life experiences. And you can just treat it as not only like a mass on a spring, but this is exactly the same motion that happens when you're on a swing set. You're on a swing set and you swing like this. At that point, you reach the maximum amplitude, which is some big angle like 40 degrees, say, or 1 radian. And at that point, your velocity is 0, but your force is a maximum, because all you have acting on it is the tension in the rope or cable or chain, and the gravitational force this way. They add up to give you a total force this way, and that force is at a maximum, because in fact it's at the largest angle difference between the tension and the gravitational force. And then as it goes like this, the angle between gravity, which is straight down, and the angle between the tension, which is almost straight up, they're getting closer and closer and closer. So the two forces are fighting each other, and the net force is decreasing. So the net force was a maximum at that maximum amplitude, and therefore the net acceleration was a maximum at a maximum amplitude. And the force goes down, 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 but it's still applying a force, applying a force, applying a force. When it gets right here, the tension is straight up, the gravity is straight down. They're canceling each other out unless the cable's too weak or gets slack. So the actual acceleration at this point is 0, but the velocity is a maximum. So as you go by the ground, you're going your absolute fastest. And then as you start to go up, you slow down, slow down, slow down, slow down, slow down like this. And now you're at a maximum acceleration again, but in the other direction. That's also a 0 of velocity and a maximum of amplitude. So you see, this does exactly the same thing as the spring does, only it's an entirely different type of motion. Okay. Any questions on how that works? Now, the other equations we'll need to use are, we've got Hooke's law. We also know that the potential energy, does anybody remember the formula for potential energy of a mass on a spring? I'll give you a hint. There's my hint. It would have been chapter 8. Also chapter 7, but 7 and 8. Okay. It's 1/2 kx squared. Now, remember, if we're talking about energy here, we're taking a spring where when it's all the way stretched, all the energy is in the form of U equals 1/2 kx squared, which is literally just 1/2 ka squared, where a is the amplitude. Then when the spring pulls the mass back and it hits the origin, the velocity is the maximum there, and the potential energy is zero because the x is zero. So what we see is, since the velocity is a maximum, this must be a sloshing of energy back and forth between potential energy and kinetic energy, and that's 1/2 mv squared. Okay, so the Vmax happens at x equals 0, and the x max is the amplitude, and that happens when v equals 0. So those equations we'll need as well. Now we're ready to roll. Okay, so let's start off with a simple harmonic oscillator. Simple harmonic oscillator, SHO is another thing they use for it. So in this case, we're going to use Newton's second law, and Newton's second law says the summation of the forces is equal to mass times acceleration. But in this case, the force, and therefore the position as a function of time, the velocity as a function of time, and the acceleration as a function of time are all not constants. They're all actual functions. Okay, so we can't use ma, we have to use m dv dt. Luckily, the mass isn't changing, so I don't have to use dp dt like we did in the momentum chapter, but I do have to use this, or I can say m d2x over dt squared, again, trying to keep the vectorness of it. So when I do that, what I'm going to get is m d2x, reducing it to one dimension, or two dimension basically, so we don't have to do vectors anymore. M d2x over dt squared is going to equal negative k times x. Okay, this is what we call a second order differential equation, but it's not the form that we normally use it. I could go ahead and write m d2x over dt squared plus kx, and then that's equal to 0. And that's all well and good. But now the next thing I'm going to do is divide by m. So when I do that, I now get this expression, d2x over dt squared plus k over mx is equal to 0. This is called a second order. That's because the highest derivative you see is 2, a second order derivative. Second order linear. It's linear because you don't see any derivatives dx dt times dx dt. That square there is showing a second derivative. It's not showing the square of a derivative. You're not seeing, stuff like that in there. And it's also homogeneous. Differential equation. And it's probably about the third differential equation you'll study when you take differential equations. The reason why it's homogeneous is you've got the function who you're taking the derivative of, in this case x. You've got it, all its derivatives and its non-derivatives all on one side of the equation. On the other side, you have 0. That's what makes it homogeneous. Okay, so hopefully that little arrow will help you. Now, if you're taking a differential equations class, they would say any function whose derivative is just another version of the function and whose second derivative is yet another version of the function and another, any of that would actually work, because you see you're going to have some number times a function plus some second order derivative. So if the first derivative is just like the function itself, then you take the second derivative, that's going to be just like the function itself. So the natural thing for them to use is say, let's let x of t be equal to a e to the rho t. And that's pretty much what they teach you in the differential equations class. And it works great. It even allows us to learn like what happens when you raise I to or e to the I power. But in the physics world, we know what the result's going to be. It's going to be sinusoidal motion, and we can just guess what the solution is going to be, plug it in, and see what happens. So we're not going to do that. We're going to say let x equal a cosine omega t plus phi. Well, from experience, we know that the omega is going to be a ramification of the equation itself. So that's not a free variable that we have to address. It's just making it solve the actual equation is going to define omega sufficiently. But you see this is a second order derivative. How do you undo a derivative? What mathematical operation undoes a derivative? Anybody?
Integration.
Exactly. And when you integrate a function without, range of integration, you introduce a constant of integration, right? So if you look at this, it's a second order differential equation. That's probably enough for you to realize, I bet you I'm going to get two constants of integration on here. And that's right. That's why I have to have an A as one of my variables and a phi as another one of my variables. Okay. That gives me enough freedom to make sure I can satisfy the initial conditions. All right. Now, when I plug this in, it's actually pretty straightforward. So dx dt is going to be the derivative of cosine is negative sine. So I get negative a. I leave a space for a reason. Sine omega t plus phi. Okay. Now I've taken the derivative of sine with respect to its argument. The chain rule says now I got to take the derivative of the argument with respect to t. That's the chain rule. The derivative of omega t plus phi with respect to t is just omega. So I get negative a omega sine omega t. That also gives me, by the way, this is v, because anytime you take a derivative of the position with respect to time, you get a velocity. Now I'm going to get a second derivative, which in this case is the acceleration. Now I take the derivative of negative a omega sine omega t. I obviously have a negative a and an omega there. The derivative of sine is cosine. Now I've got to use the chain rule again. And the chain rule would say that I now have to multiply by another omega because still the derivative of omega t plus phi with respect to t is omega. So now I get negative a omega squared cosine omega t. Okay. So just by me reminding you that that is v and the other one's a, hopefully you can recognize that this must be v max and that this must be a max. Right? Because I told you how all this is going to go. You have a cosine function as the x, you're going to have a negative sine function as the dx dt, which is the velocity, and then you're going to have a negative cosine a negative cosine for the acceleration as a function of time. So again, the thing out in front of the trig function is the amplitude, and the max amplitude is called a max or v max or x max. Okay, now that I have those, I can plug them into the differential equation and I get negative a omega squared cosine omega t plus phi. So that's for the first derivative, or excuse me, for the second derivative, the first term is what I was saying. And then plus k over m times the zeroth derivative, which is just a cosine omega t plus phi, and now that's equal to 0. So that's what I did. I just plugged those in. Now I have a common factor of a cosine omega t. So I'm going to go ahead and say a cosine omega t plus phi times k over m. Just putting the positive term first doesn't matter because it's addition, so you can do it in any order. Positive term first is k over m minus, darn it, minus omega squared is equal to 0. This has to be true for all time. So that means this part must be 0. So automatically we get omega is equal to, it should be the plus or minus square root of k over m. But since we're going to treat omega like it's an angular frequency, a negative would not make any sense in terms of this type of problem. So we just take the positive one. So as I suggested, the omega is just fixed by the equation itself. That's a key result. Okay. Now we have to have initial conditions to figure out the A and phi. We must have two initial, we call them initial, but in principle, they could be the position at x equal 0.7 seconds and the position at x equals 72 seconds. In principle, that's enough for us to figure out the two constants. But we normally will take the position at t equals 0 and the velocity at t equals 0, in which case they really are initial conditions. So we have to have two initial conditions. Darn it. To compute, actually. Oops, not A. I used a uppercase A. And phi. That's called the phase angle, by the way. That's often called the phase angle. Okay, so that's what we have to do, but we now have a solution. Now, some people get the idea that physicists are really preoccupied with springs, but that's not really the case. It just turns out that if you're looking at a potential energy function anywhere near an equilibrium, then that is like a minima or a maxima, right? And what's the derivative of a function at a minima or a maxima?
Answer the fucking question.
Isn't it 0?
Yes, exactly. So what that means is the derivative f of x or u of x or whatever near that equilibrium spot, the derivative of that is going to be 0. Now, we can use the Maclaurin series. There's a Taylor series and a Maclaurin series. The Maclaurin series is where we expanded about 0. The Taylor series is where we expanded about A. So I'm going to say u of x, the potential energy function, according to Maclaurin, is 1 over 0 factorial times u, the 0th derivative of it. Notice I put it in parentheses. That's going to be evaluated at x equals 0, and then I'm going to multiply it by x to the 0 power. Then the next term is 1 over 1 factorial u prime evaluated at 0 times x to the 1 power plus 1 over 2 factorial u double prime at 0 times x squared plus dot dot dot. Okay. So if we're looking near here, u prime is approximately equal to 0. Remember how when we were doing potential energies, we could count the ground level as u equals 0. But if we did a roller coaster problem, we could say, well, the roller coaster, the lowest point is about 6 meters over the ground. Let's call that the 0. That's equivalent to just adding any scalar to the potential energy function, right? So if you look at that, and then you consider this could just be a scalar added to the function. Okay, because the function will have some value at 0. 0 factorial is defined to be 1, by the way. X to the 0 is 1. So this is just some constant. But this one right here is approximately 0. Right? Now, when you get over here, what you realize is this is just the second derivative evaluated at 0, and therefore is just a constant that we might wish to call k. And of course, 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. But 2 factorial is just 2 times 1, so it's just 2. So what we get here is 1/2 kx squared. So the fact that near an equilibrium point, the potential energy for any function is essentially a constant plus 1/2 kx squared tells us that a mass on a spring, is a good representation of anything near its equilibrium point. And in fact, that was one of the first things we did when we discovered the Schrodinger equation, is we applied it to a mass on a spring to approximate what the energies would be like for adjacent atoms. Okay, so that's why we study them so much. Does that make sense? Now, in general, how do you evaluate the initial conditions? Well, we already know something. We know omega is equal to square root of k over m. One example is like the example we did first, which is where I started it with x of 0 is equal to x max, which we're going to just define to be a. Okay, but dx, well, that just worked out ugly. But dx dt, which is v of 0, is going to be actually 0. So when I do that, what I'm saying is x max equals a cosine of 0 plus phi. And if this is the case, that tells us something very good. If I were to choose a to be x max, that would be okay depending on what phi is. But in this case, I need cosine to come out to be 1. Otherwise, it's not necessarily going to be very easy to deal with. So this tells me I'm going to let phi equal 0 or plus or minus 2 pi or dot, dot, dot. I'm going to choose 0 because that's easier. Okay. So that's what we're going to use. And now I can combine this with this to say that 0 is equal to negative a omega times sine of 0 plus 0. remember we chose omega equals 0, and therefore this automatically sets that up to be that way. Okay. So the phi being 0 is right, but this causes A to be equal to X max. So now we can say X of t is actually equal to X max cosine omega t plus, oh, excuse me. In this case, it was just omega t. And that's for these initial conditions. Of course, you can also have initial conditions of V of 0 is equal to V max, and X of 0 is equal to 0. In that case, what we're going to have for this one is 0 is equal to A cosine 0 plus phi. For this one, we're going to have V max equals negative A omega sine 0 plus phi. Okay. Now, in this case, we want sine to be 1. So that implies phi is going to be plus or minus pi over 2 plus or minus 3 pi over 2 dot dot dot. I'm going to choose the positive phi equals pi over 2. Okay, that should work. And of course, pi being positive, or phi being positive pi over 2 means the cosine is going to be 0. You sometimes might have to choose a plus or minus based on whether the Vmax is in the negative direction or the positive direction. In this case, for instance, that's a good case. So in this case, I actually need Vmax sign to be -1. So let me correct that. I want it to be -1 so that I'll just have A omega equal to Vmax, in which case I'm going to change this to negative pi over 2. Okay. So now I can say from this guy and this guy, I can say 0 is equal to A times the cosine of negative pi over 2. And looking at our cosine, it's supposed to look like that. This is pi over 2 right there, and this is negative pi over 2 right there. So you can see in that case, it's going to be 0. So that makes this equal to 0, and that's exactly what we wanted. Okay, so for this one, I got X of t is equal to A cosine omega t minus pi over 2. And of course, that also tells us, actually, that also tells us that A omega is Vmax. Which is what we got here. But by making that phi negative pi over 2, the sign of it was -1, and therefore that canceled out the negative, so I could get the actual A times omega being Vmax. And they said Vmax, that would be like a positive number they'd give you, so it really wouldn't make sense to have a positive number equal to a negative number. So that's the actual function with that one. In general, it never has to be any of that. In fact, all you might have in about the most general case is x0 equals x of 0, and V0 is equal to dx dt evaluated at t equals 0, that means x0 is equal to a cosine phi, and V0 is equal to negative a omega sine phi. Okay, so if I divide V0 by x0, then what I get is negative a omega sine phi over a cosine phi, which is just omega tangent theta, or excuse me, tangent phi. So phi is going to be the inverse tangent of, you can see now it should be the inverse tangent, it should be the inverse tangent of V0 over omega x0. Now that you have that, you can go ahead and use the other one and find out what the A would be. So A, actually, let me keep it in black. So A would be, for instance, x0 over cosine phi. We can, in fact, imagine a triangle. The triangle would have this side being V0 and this side being omega x0 and this being phi. Then this would be the square root V0 squared plus omega squared x0 squared, like that. And then cosine of phi would be adjacent over hypotenuse. So we would get, in fact, the hypotenuse would be on the bottom and the bottom, so that becomes the top. So I get x0 times the square root V0 squared plus omega squared x0 squared. All of that divided by omega x0, and you can see the omegas, the x0s now cancel out. So now I'm left with finding A is actually equal to the square root of omega squared x0 squared plus V0 squared, all that divided by omega. So that's the general initial conditions that you could possibly solve. So that's all the different initial conditions you can actually do. If you were to look in your book, you'll see examples like this one, the simplest of all of them. It says, when a family of 4 with a total mass of 200 kilograms step into their 1,200 kilogram car, the car's spring compresses 3 centimeters. A, what is the spring constant of the car's springs, assuming that they act as a single spring? And B, how far will the spring lower, or how far will the car lower if it's loaded with 300 kilograms rather than 200 kilograms? So that's a typical problem. Let me show you real quick how that's worked. And this is really 14.1. It's literally straight out of the book. Okay, what we see is 300 kilograms, or excuse me, 200 kilograms. So 200 kilograms causes a compression of 3 centimeters, and they want to know K equals question mark, that's part A, and then part B, x2 equals question mark when m2 is equal to 300 kilograms. Now you can see it's 1.5 times, because if you take half of 200, you get 100. If you multiply 1.5 times 200, you get 300. So we probably expect the linearity to make this to be 4.5 centimeters. That's exactly what it is. So let me show you how to do it. without that quick figuring. So for part A, we're going to say the force, which is, by the way, not 200 kilograms. The force is 200 kilograms times 9.8, which would be 1,960 newtons, is equal to, notice how I dropped the negative, it's equal to K times 0.030 meters. Notice how I also converted to meters. So K is going to be, I think it's 6.4 times 10 to the fifth or something like that. Let's see. 1960 divided by 0.03 is 6.54. That's it. So 6.5 times 10 to the fourth, and that works out to be newtons per meter. That's the spring constant. Notice that is also the typical unit for the spring constant. Now for part B, they're saying now that we know that, what's going to happen? Well, in this case, I'm going to take 300 kilograms and times 9.8. That's going to give me 2,940 is equal to 6.53. I've got it underlined since we only had 2 sig figs, times 10 to the fourth newtons per meter times x. So in this case, we get x is equal to 0.045 meters. Does that make sense? Now, that's pretty straightforward, but you can go on further from that. So for instance, I'm not going to do this one. Another example they do is they go back to that same car and they say car springs again. Determine the period and frequency of the car in this example. So example 14.2. It's actually 14.3, sorry. Determine T, whoa. And F for the car. Now remember, they said the mass was 1,200 kilograms for the car. Okay. And what we're going to do is assume the initial 200 kilogram people were in there. So I'm going to say M1 equals 200 kilograms. Okay. So that means M total, which is what I'm just going to call M, is 1,400 kilograms. We know omega is the square root of K over M, and we know that's equal to 2 pi over the period. So we can say clearly the period is 2 pi over omega, which is 2 pi times the square root of M over K. So the period for this must be 2 times pi times the square root of 1,400 kilograms divided by 6.53 times 10 to the fourth newtons per meter. When I do that, I'm going to say 1,400 divided by 6.53 e to the fourth. That's 0.02. I'm going to take the square root of that, and I'm going to multiply it by 2 pi. And that gives me 0.91999. And all of those are extra sig figs. So that is the period of this. So you can imagine sort of an Uncle Buck style car going boom, boom, boom. If you haven't seen Uncle Buck, you need to. All right. Now the frequency is just 1 over the period. So all we have to do now is take this and raise it to the -1 power. And that gives me 1.09 hertz, with one extra sig fig. Any questions on that? So that's another typical example, but you can already see how we can just sort of apply these equations over and over again. In fact, example 14.4, it says a spider of mass 0.30 grams waits in its web of negligible mass. A slight movement causes the web to vibrate with a frequency of 15 hertz. Estimate the value of the spring stiffness constant, K, for the web. And then part B, at what frequency would you expect the web to vibrate if an insect of 0.10 grams is trapped in addition to the spider? So that's another great example. And this is 14.4. We have M1 is equal to 0.30 grams, which equals 0.0003 kilograms. And M2 is equal to 0.0004, and actually this could be another zero after that, kilograms. And what we say is F1 is equal to 15 hertz. So what we want to know is part A, what is the spring constant, and part B, what is F2? Okay, not much time left. So with this solution, what we're going to do it
Get that. Could you try again?
with this solution, all we're going to do is use omega equals 2 pi f, and that's equal to square root of k over m. And when I do that, I can see that k is going to be equal to 2 pi f squared times m. So for all this is for part A. So K is going to be equal to 2 times pi times 15 hertz squared. The 2 pi's got to be squared as well, times times 3 times 10 to the negative fourth. And that gives me 2.7. And of course, the K is newtons per meter. Okay. Now with the other one, we're going to say part B. Whoa. Part B, we're going to say omega equals 2 pi f again, but now we want to know f. So f is going to equal omega over 2 pi, and omega is square root of k over m. So I'm going to say 1 over 2 pi times the square root of 2.7. It would help to use an extra sig fig here, but I just stole the one from the numbers, divided by 0.00040 kilograms. And when I do that, I'm going to get a different answer. This is going to be like 13 hertz. Okay. So that's some of the problems we can do. Now, we've actually run out of time. What I'm going to tell you is go ahead and finish reading up chapter 14. Next time I have some videos for you guys that I'll make that you can watch too to see some more examples. But basically what I'm going to do from this is I'm going to show you another couple of instances where the same differential equation pops up. And that's in the case of a pendulum. It's also in the case of what we call a physical pendulum, and it's also in the case of a torsion pendulum. All the same equations come up, and I'm going to examine it from a energy standpoint, which your book does as well. After that, then I'm going to go to a damped harmonic oscillator, where instead of having the differential equation just be d2x over dt squared plus k over m times x equals 0, there's going to be another term that's a force, negative b times velocity. That's the drag force. And of course, velocity is dx dt. So now we're going to have an equation that looks like, just let me write it real quick and then I'll let you guys go. The next equation for the damped harmonic oscillator is going to be plus B dx dt plus k x is equal to 0. Oh, there's an m here. And this ends up becoming d2x over dt squared plus b over m dx over dt plus k over m x is equal to 0. And we're going to do the same stuff. We're going to take a guess at the solution. We're going to get a different omega. And then that omega is going to allow 3 different scenarios because it comes out to be a quadratic equation. And you know the quadratic solution is b squared or negative b plus or minus the square root of b squared minus 4ac over 2a. There's a case where it's a non-real number, meaning the square root's a negative number. There's a case where the square root's a 0, and then there's a case where the square root is a positive number. That's the 3 scenarios we're going to get. You guys are free to go. I saw that Ariel came in, and just want to remind you, I did send that email about your exam, so make sure you follow that. Keep an eye out for emails. I will be emailing you. Maybe I might not email you to tomorrow, but I should have the practice final put up tonight. If it's not tonight, it'll be out. Well, if it's not really soon, it'll be out first thing in the morning, but it probably will be up sometime tonight, just late. So have a good one, everybody. Thanks for coming. Make sure you find out from Maria or your instructor for lab what time you're supposed to have your course final. And if you let me know, that'd be helpful. I'll just make sure I get it ready for her as well. Have a good one, everybody. Thank you for coming. Don't forget to chat your first and last name. It looks like most of you already did.
Thanks.
Thank
Have a good
you.
one as well.
You're welcome. Thank you. Thank you, Jake. Ariel, I saw that you missed today. Did that
Hey,
email?
Professor. I did get the email. The HRBT was blocked for more than an hour by the
Oh,
time I was ready to leave out.
I wondered what happened, but the main thing is now it's automatically the final will be on the 24th. Does that mean you don't have to do anything special now because you're leaving early enough?
I would have left probably like Sunday or Monday before that if I could,
Okay,
because
so
I think I
you're leaving this Sunday?
if I can.
Okay, gotcha. Yeah, that's not a problem. We can still set it up the other way. I was thinking it was the previous Sunday that you're leaving, but or the following Sunday that you're leaving. But if you're leaving this coming Sunday, then yeah, even the 24th isn't going to help you.
Yeah, if I could, if that can work.
Do you think you can take the test either Friday or Saturday? Because I know the testing center has hours on Friday and Saturday.
I think if I rush to do it this week, I might end up shooting myself in the foot.
Gotcha.
I feel like
Okay, so you want to wait till you come back?
I could, or would lockdown browser be okay for you? Which one would you prefer?
It's got to be lockdown browser with a good internet connection and a camera and a mirror. If you can do that while you're away, that'd be great. I have no problem with that whatsoever.
Okay, yeah, that could work. Because we have internet connection at the house, so there shouldn't be any problems. I guess if when I get there, if the internet seems really sketchy, I could probably send you an email
Yeah,
just to
that's fine.
confirm.
Yeah.
Okay, so I could confirm whether it's okay to do it the 24th or the 29th, like depending on how prepared I feel.
Yes. Yep.
Okay.
I'll just give you that. Yeah, I'll give you both of those days. You can do it either one, and I'll set it up. And I don't. I'll probably have a second one, a separate one for people that's taking it online, and it'll like have your name in it or something.
Okay. Okay.
Okay.
All right. I think that works.
All right. Well,
All right.
you might want to watch this video because this is actually no, you're 242, right?
Yeah, I'll go in and look for, because we're gonna have class on Monday next week.
Right.
So I'm gonna go in and look for the videos for today and also coming Monday so I can keep up with what went on in class.
No problem. I just went back over Ampere's law again. Did this. In fact, I did the solenoid. I did the straight wire, and then I did a couple more problems too with Ampere's law. Then in fact, I got all the way through chapter 30.
Oh, okay, okay.
It was a
Alright,
lot.
so
That was why I was bummed out that you didn't make it. But I did it over the whole lab time. I took the whole 3 hours. So
did it, okay.
I'll post some
Okay.
videos that are relevant, and that way you won't be lost.
All right, thank you. I appreciate that.
All right. Have a good
All
one.
right. Thank you. You
Bye-bye.
too. All right, bye-bye.